All right, let's begin by building a tool chest of our analysis techniques. But before we begin, it's worthwhile asking the question, what does it mean to analyze a circuit? Well, analyzing a circuit simply means find all the element V's and I's. In other words, find all the branch variables. And so what are these branch variables? Well, if you look at element R1, I can write its branch variables as plus minus V1 here, so the voltage across R1, and I can assign a current I. And for R4, as an example, I can say there's V4 and there's I4. And in general, I'm pretty free to assign voltages and currents with in any direction, but you will notice that I'm going to follow a discipline where I'm going to draw the current entering into the positive terminal, and I'll show you why in a quick second. So as another example, I can define the element values for the voltage source. The branch variables here would be V0 and a current I0 going here, and so on and so forth, and I can do the same for all the elements. So analyzing a circuit really means go find all the element V's and I's for the circuit. We are now ready to start with our analysis techniques that will go into our tool chest. The first method that we will look at is called the very basic KVL KCL method of circuit analysis. And as I mentioned earlier, our goal with circuit analysis is to find all the element V's and I's. The KVL KCL method is extremely simple. In the first step in this method, you take your circuit and you write down for each element their VI relationships. Then, as a second step, you pick all the nodes, and for each node, you write KCL. Then, as a third step, you go through the loops one by one, and you write KVL for each of the nodes. Notice that each of these equations is a very simple equation containing simple algebraic expressions of the currents and the voltages. Now, you will end up with lots and lots of equations, and you will have lots of fun solving them. Well, let's take a look at an example. So our goal, as I said earlier, was to find all element V's and I's. Now, before we go in and do an example of using the KVL KCL method, I want to spend 30 seconds telling you about a couple of ideas on how to label element V's and I's. So for example, here's an element, okay, the element E in some circuit, and notice it has a V and an I. In general, what we're going to do is we are going to follow a little discipline or a little convention in how we assign the voltages and currents. Specifically, we're going to take the current to be positive going into the positive voltage terminal. So in this case, here is the positive voltage terminal of the element E, and so we're going to be assigning currents to be going into the positive voltage terminal. Now, you can do whatever you want. It really doesn't matter. You can go and assign currents and voltages any which way and reverse them, and KVL, KCL will simply work. It just turns out that in a lot of what we do in circuits and electronics, it is useful to follow conventions so that you don't make silly algebraic mistakes. So whenever you have a choice of being able to do something 10 different ways, it is just good to be disciplined and use one technique all the time so that you just don't make mistakes. Now, one benefit of taking the current to be going into the positive terminal of the element is that the power consumed by the element, which is given by VI, is positive. Okay, so if you choose your convention of the current going into the positive terminal, then the power consumed by the element VI is going to be positive. So this way, or this convention of assigning voltages and currents as your branch variables is called the associated variables discipline. And again, as with all disciplines, it's something we impose on ourselves. It's a convention, okay? We just follow this convention to simplify our lives and to reduce the chance that we're going to make mistakes. And if you don't like this, don't worry, go ahead, make my day, pick different conventions for V and I, just be careful. If you follow this convention, it is less likely you will make mistakes. Now, before we actually begin the KVL method, there is one more thing that I need to quickly cover, which is a few element relationships. So you've seen resistors before. So for a resistor with a resistance value R, the VI relationship is simply given by V equals IR, where if this is my voltage V and the current I, V equals IR. Next, for a voltage source, let me draw out a voltage source with voltage V0 in this case, and let me assign branch variables V plus V and minus V, and the current I, then the element relationship V is given by V naught. One of the places where I find students getting confused is the difference between element values and the component value itself. So if you look at a voltage source of this sort, a V0 is a property of this voltage source. Okay, so if it's a battery, it might supply a voltage V0 of 1.5 volts. However, when I take this voltage source and I put that into a circuit, within the circuit, it's going to draw some current I, and there'll be some voltage across it. Yeah, if there's a resistor, it'll be some other voltage. But if I put this voltage source with an ideal voltage source with the internal voltage V0 and I stick that into a circuit, then the branch variable V associated with that will also be equal to V0. But in general, that doesn't have to be true. Next, let me go to a current source. In this case, I'm going to define my current source like so. I can also apply its branch variables V and I, and the equation, if the current source supplies a current I naught, then the element relationship for this is given by I equals I naught. Okay, so these are three examples of element relationships for resistors, voltage sources, and current sources. Okay, we're done with the preamble. We are now all set to dive into method one of circuit analysis, the KVL KCL method. So let's apply this method to the demo circuit that we used earlier, and let's see how we can find out all the element V's and I's. Now recall, the KVL KCL method said, in fact, circuit analysis said, that solving a circuit involved finding all the element V's and I's. So why don't we start this example with labeling all the V's and I's for our demo circuit. Okay, so let's get started and very quickly label all the branch variables. And I'm going to follow associated variable discipline in doing that. So let me start by labeling all the branch variables. So let me call this V0. Current is I naught coming in here. Let me call this V1, and let me say this is current I1. Let me say this is V4, current I4. Let me say this is V3 and current I3. Let me then say that this guy here is the V5 and current is I5. In this case, it's V2 and the current is I2. So I have a bunch of branch variables assigned, and I also have, and these branch variables involve both the currents and voltages. And notice here that in this example, I have used the associated variable discipline, but I've assigned all my currents flowing into the positive terminal of each of the assigned branch voltages. So here I get 12 unknowns in all. If you count V0, V1, V2, V3, V4, and V5, that's 6. And I0 through I5, that's another 6. So I have a total of 12 unknowns. Also notice that A is a node, B is a node, C is a node, and D is a node. And so those are my nodes. I will be writing KCL for those nodes. And then I have a bunch of loops. So what are my loops here? So I have a loop L1, I have a loop L2, I have a loop L3. Now I claim there is one more loop. Right? Let me pause here for a second and have you think about where that fourth loop is.